Uh, Good evening. So we'll start with the this week live session content. So um, yeah. So in week three, the lecture video starts with the concept of dot product. So if you take any two vectors, say u and v, which has value u1, u2, and v1, v2, this is in R2. Then the dot product is defined as the sum of their uh, products. So sum of the products of the individual components. That is u1 v1 plus u2 v2. That is you multiply the first element with the first element of the second vector the second element with the second element of the second vector and then add them. So this is the concept of calculating a dot product of two vectors in R2. Now when we have, so this is only when there are two elements, that is R2. Now when we have n elements, this will just increase to n components. So the 2 will become n. So just like this one. So it will be u1 v1 plus u2 v2 plus etc. up to un vn. So for two n-dimensional vectors u comma v, the dot product will be u dot v, that will reach that will be up to v1. So this is a dot product. So the dot product of a vector which itself yields the square of their norm. So if you take the dot product of a vector, say u, with u, then this is equal to the norm square of that vector. So norm, a vector norm will give the length of that vector, and so this is the same as the dot product of that vector with itself. Now there are some properties of this dot product. So one application I think we have discussed in the previous one of the previous session, that dot product is something that is used widely in machine learning. So for example, if you take the neural network itself, neural network, we use this y is equal to f of w transpose x plus d. So this is a dot product. It's not exactly a dot product, but uh, in every machine learning algorithm, there is an application of dot product. And another thing is like when comes to its meaning, it helps us to understand whether two vectors are similar or not. So how do we understand that is by looking more into orthogonality as well. So before that, coming to the properties of dot product. So if you have a vector space V that is over R, and when you have two vectors U and V that belongs to this vector space V, then it satisfies an inner product satisfies this symmetry property, that is inner product of U and V is the same as V into U. Then linearity property, that is when you have u dot alpha v plus beta w, then you can take the scalars out and then do their dot product. Similarly, the distributivity in the scalar scaling. And then finally, one important thing is this positive definiteness. That is when you take the dot product of a vector with itself, uh, it will be always greater than or equal to 0. So we have seen here that the dot product of a vector with itself is norm square. So anyway, this will be a positive quantity. And so anyway, if it is a positive quantity, then definitely it is greater than 0. Now greater than, but here we have greater than or equal to 0. So the equal to part comes when u is a 0 vector. So when u is a 0 vector, it will have 0 value. The dot product of u with itself will have 0 value. So this is the positive definiteness. Now coming to orthogonality, if before that I'll give two examples. So there are So you have two vectors A is equal to 4 minus 2 and 1, and B is equal to 1, 3 and 2. So these are two vectors in R3. You can compute the dot product between A and B. So when you do A dot B, it is this sum of product of individual components. So 4 into 1 minus 2 into 3 plus 1 into 2. This is 6 minus 6 plus 6, that is 0. Now, can you compute the norm of A and the norm of B? So you just have to take so there is a vector A1, A2, A3. To find the norm, you take the square root of A1 square plus A2 square plus A3 square. So when you do that here, you get 4 square plus minus 2 square plus 1 square. So 16 plus 4 plus 1 square root. So it is square root of 21 for the norm of A, and here it is 1 plus 9 plus 4. That is 14. So square root of 14. So you get 21 and 14. So this is how we find the dot product and the norm of two vectors. Now coming to orthogonality. So orthogonality is if there are two vectors A and U and V, and if you take the dot product of those two vectors, then if the dot product is equal to 0, then we say that the vector U and V are orthogonal to each other. So that means that there is no common information, or there is no redundant information between the two vectors. That is, they contain very distinct information. Now, so when U dot V is equal to 0, we say it is orthogonal. So here in this case, is this A and B orthogonal? Yes. So it is orthogonal because just now we found that A dot B is 0. So these two vectors are orthogonal. So then the next question is, find the value of scalar k such that the vectors u and v are orthogonal. Yeah. So you just have to apply the formula u dot v is equal to 0, and then you get 4k minus 6 minus 2k is equal to 0. That means 2k minus 6 is 0. So k is equal to 3. Okay. So there is an inner product space V, and you are given the norm of U is 5, the norm of V is 3, and U dot V is 2. So first you have to find what is the inner product 2U minus V, U plus 3V. So the norm of U is 5. We know the relation between U, the dot product of U with itself and the norm. So this will be U comma U is norm U square. This is something that we already know. The relation between the dot product and the norm. So you have to make use of this. This will be 25. The norm of V is 3. Then the dot product of V with itself will be 9. So what you have to find is the dot product between 2U minus V and V plus 3V. So you have to find the dot product between 2U minus V and U plus 3V. So this is 2U minus V, V plus 3V. This you can write it as 2U comma U plus 2U 3V minus V U minus V 3V. So using the properties that we have already discussed here, you can take it out. There's a linearity property, scalar scaling. So this one, so if you have CUV in that form, you can rewrite this as C into UV. So when you rewrite this, what do you get? 2 times U comma U plus 2 into 3 times U comma V, okay, minus V comma U minus 3 times U comma V. Now this we already have from these options, and we wrote it like this here. So you just have to substitute. So 2 times 25 plus 6 times u into v is 2 minus 2 minus 3 into 9. So this will be 50 plus 12 minus 2 minus 20. So it is 60 minus 27, that is 30. Now, there are some previous year questions. So which among the following the inner product need not satisfy? XY is X transpose Y. So the first option is, I'll write it as A, B, C, and D. You can check and tell the correct answer. Yeah, so the answer is C, that is false. So when you take option A, X transpose Y is equal to Y transpose X, this is the commutative property. It is satisfied for inner product. Just like that, similarly, this is also satisfied. And if X is orthogonal to Y, then that means that their inner product is 0. Now this always X transpose Y is greater than 0 is not true. X transpose Y can be positive, negative, or 0. All the three different possibilities are there. So if the angle between the two vectors is 0, then they are parallel or they are aligned in the same direction. If they are orthogonal, then the angle will be 90 degree. If they are completely in the opposite direction like this, 180 degree like that, then they can be negative. So there are three different possibilities for X transpose Y. So this is the correct option. So then coming to the angle between the two vectors u and v. So in consider two 2D vectors u and v, that is u is u1, u2 and v is v1, v2. Then we can write this u1 as norm u cos theta. We will put the and u2 is norm u sin theta, and v1 as norm v cos theta plus phi, and v2 is norm v sin theta plus phi. I think this you might have seen in the lectures, that you can write the dot product as the norm of u into norm of v into cos phi, which is the angle between these two vectors. Now, when the angle between these two vectors is 90 degree, then you say that the vector u and v are orthogonal to each other. There is a zero vector property where a zero vector is orthogonal to every vector in the inner product space. Now, if we have two vectors that are where their angle is either 0 degree or 180 degree, that is either they are in the along the same direction or they are along the opposite direction, that is the angle is 0 or 180 degree, then uh, sorry, that is the equality condition. Okay, so there is an inequality called as Cauchy-Schwarz inequality. That is, the magnitude of the inner product of two vectors is bounded by the product of their norm. So, when you take the inner product and the magnitude of it, the maximum it can take will be the product of their norms. And so it will be always less than the product of their norm, and it will be equal to the norm when they are in the same direction or the opposite direction. That is, their angle between them is 0 degree or 180 degree. So this is the Cauchy-Schwarz inequality. So you have two vectors 2, 1 and v is equal to 1, 3. It's an R2. Find the dot product u dot v first. Yeah, so it is 5. 2 into 1 plus 1 into 3 is 5. Find the angle, cosine of the angle between u and v. So the angle between is given by u dot v by norm of u into norm of v. Yeah, so it is 1 by root 2. What is the norm of u? What is the norm of v? This is root 5. This is root 10. So this is root 2 into root 5 we can write. So u dot v we found that it is 5. So 5 by root 5 into root 2 into root 5. So root 5 into root 5 is 5. So this will get cancelled. So it is 1 by root. Now you have to verify the Cauchy-Schwarz inequality for U and V. So you just have to substitute this. So you have to find U dot V is less than the product of the two vectors. So the left side is 5 and the right side is norm U into norm V, that is root 5 into root 10. So that is root 5 into root 5 into root 2, that is 5 root 2. So that is around 7 point something. So you see that 5 is less than or equal to 7.07. Okay. Now, orthogonal complement. So if there is a subspace W that's a subspace of a vector space V, then the orthogonal complement of W is denoted by this W perpendicular. That means that when you take any vector U from the full vector space V, that means you have a vector space V and you have a subspace here. This is your W, and then you have a subspace called as W perpendicular. Then you have, let's call any vector in the capital W as the small w, and any vector in W purpose U. Then when you take the dot product of any vector in W with any vector in W perpendicular, or W, the orthogonal complement of W, then what you get is 0. You get is 0. That means every vector in the subspace W will be perpendicular to every vector in its orthogonal complement. Okay. So, yeah. So then there is a proof to show that this is a valid subspace of V, and we can show this by taking the closure under addition plus under scalar multiplication and checking whether zero vector is there or not. Now there are 4 different subspaces, 4 fundamental subspaces that we have: the row space, the null space, column space, and left null space. The row space is where you have for every y. So there is a real, actually there is a real matrix, and the dimension of the matrix is given by m cross n. So when you take any vector from Rm and multiply by the A transpose Y, you get a set of vectors. When you apply this transformation A transpose, that is the row space. Null space is where the matrix A will make a set of vectors x to 0. X is equal to 0. Then column space is all the linear combinations of the columns of A. This is A. Then left null space is where all the y vectors that will lead to, all the vectors y that leads to 0, then apply the transformation A transpose. So this four are the four fundamental subspaces. Now coming to orthogonal and orthonormal basis. So for an n-dimensional vector space V with basis vectors u1, u2, etc. up to un, an orthogonal basis is where all the distinct pairs of vectors are mutually orthogonal. So the uh, vectors will be mutually orthogonal to each other in that basis, and it becomes an orthonormal basis when every vector has a unit length. So in an orthonormal basis, the vectors that belongs to this basis will be orthogonal basis. The vectors that belongs to this group, this set, will be orthogonal to each other, and it becomes orthonormal when the length of each of that vector in the set is equal to 1. So one question is, find an orthogonal, this question, find an orthogonal complement subspace for W, that is a subspace in R3, and it is given by span by W is equal to 1 minus 2, 3. So you have to find the basis for W per. So I will just help you to start with. So we studied that W curve will have set of vectors. Let's call them as X, and X is in R3 because W is also in R3. So W curve has vector. It consists of all the vectors X that is equal to X1, X2, X3 such that X times W will be equal to 0. That is, when you take any vector X that belongs to W curve, we say that this is an orthogonal complement when for every vector that you take from W curve and every vector W that you take from W will be equal to 0. So this is what is to be found. So that means we will have x1, x2, x3 times W is given by this 1 minus 2, 3. This is equal to 0. Okay. When you find this, you get an expression. You get expression, but you have to rearrange it such that you get an expression for the base. Okay. So when you find the dot product, what do we get? We get x1 minus 2x2 plus 3x3 is equal to 0. So you can write this as, write x1 in terms of x2 and x3. So we get x1 is equal to 2x2 minus 3x3, right? So, this is the actual vector that we started with, x1, x2, x3. Now we can, instead of x1, we can rewrite it with this expression. So we get 2x2 minus 3x3, x2 and x3. So x2 and x6. So this is the uh, expression for a set of vectors x in the orthogonal complement of W. Now we have to find what is the basis. So x2 and x3 are free variables here. So you can take them out and write it as x2 times what is there? 2, right? This is x2 times 1. So 1 into x2. Here there is no x2 term. So it is 0 plus x3 times, this is minus 3. There is no x3 term here. So 0 and x3 is 1. So now we have to factor out the free variables. So 2, 1, 0 minus 3, 0, 1. This is the basis for the orthogonal complement of W. So that means you take any combination of this one, any that is any scaled version of this number and this number, this vector and this vector, and multiply it with the W value, you get 0. So this is the basis for W. So it's like you start with taking any set of vectors x, that is x1, x2, x3, because it is an R3, multiply it by W, the expression that is given for the subspace W. You get this expression. You simplify it by taking out x1. Then you rewrite it here for x1. Then you move the free variables, because now you know that x2 and x3 can be any value. Take it out and rewrite it in terms of x2 and x3. So this is the set of bases. So you have, we'll do this one. You have a matrix A, 1, 2, 1, 2, 4, 2. What is the basis for the row space and null space? So here, first you see that we have this first row and second row. So we have two vectors. The first row is a multiple of the second row, right? So it is 1 into 2 is 2, 2 into 2 is 4, 1 into 2 is 2. So first we have to uh, make it in reduced echelon form. So when you do that, what do you get? 1, 2, 1. So this is R1, this is R2. So R2 minus 2R1 will be 0, 0, 0. So now this is your A. It is in reduced echelon form. Now what you have to do is the A transpose is the row space of row space. So A transpose will be 1, 2, 1, 0, 0, 0. And the row space of A transpose will be the number of non-zero columns. So that is 1, 2, 0 column. So the row space will be 1, 2, 0. Now for the null space, this A transpose X is equal to 0, right? So that is the, AX is equal to not A transpose, AX is equal to 0. So that is uh, X1 plus 2X2 plus X3 is equal to 0. That is this part. So this is 1, 2, 1, 0, 0, 0 into X1, X2, X3. That is A into X is equal to 0. So we get this expression when you do this multiplication. X1 plus 2x2 plus x3 is equal to 0. So just like we have done here, if you have understood this, then can you tell what is the basis here for this expression? So you have x1 plus 2x2 plus x3 is equal to 0. What will be the two vectors that you get as the basis for the null space? Yeah, that is correct. So x1 is equal to minus 2x2 minus x3. Then you write it in x1, x2, x3 form. We get minus 2x2 minus x3, x2, x3. Then you can take out x2 and x3. So we get x2 times minus 2, 1, 0 plus x3 times minus 1, 0, 1. So then the basis will be minus 2, 1, 0 and minus 1, 0, 1. Okay, I hope this is clear. Now we can do this one. So you are given two vectors v1 and v2. First, you have to confirm that this is a orthogonal basis. How do we confirm? whether these two are orthogonal or not. Their dot product should be equal to 0. So, is it 0? Yeah. So, their dot product is 3 into minus 4 plus 4 into 3. So, they are orthogonal. Now, you have to, are they orthonormal as well? No, they are not orthonormal. So, you have to convert it into an orthonormal basis. So, can you convert it into orthonormal basis and tell what are the vectors? So, to convert it into orthonormal basis, what do? V1 divide by the norm of V1 and V2 divide by the norm of V2. Yeah. So, in both cases, it is square root of 3 square plus 4 square, which is 5. So, it will be 1 by 5 times 3, 4 and 1 by 5 times minus 4, 3. So, this will be an orthonormal basis. So, so you have two vectors. Now, a set of vectors is uh, called as an orthogonal set when all the vectors in every distinct pair of vectors is perpendicular to each other. Similarly, if every set of vectors is orthogonal and every vector has a unit length, then it is an orthonormal set. So, orthonormal basis is where the normalization is also done. Now, so you are given three vectors in R3, V1, V2 and V3. So you have to find coefficient B and express this B in terms of the orthonormal basis. So there is a orthonormal basis expansion theorem that says that if you take any vector B in the vector space, then B can be expressed as a linear combination of the orthonormal basis vector. So here that B is given as 1, 2, 3 and you have to find the coefficients for B in terms of this vector, that is this coefficient terms. I think we will try this after the previous year question. Which of the following is true if U and V are orthonormal vectors? U dot U will be greater than 1, V dot V will be greater than 1, U plus V dot V will be greater than 1, U plus V into U minus V will be 0. This is A, B, C, D. Yeah. So it will be U plus V into U minus V is equal to 0 because that will be U square minus, sorry, the norm is always 1. So that will be, when you take the subtraction, it will be equal to 0. Um, Identify the correct orthogonal complement pairs with respect to four fundamental subspaces of matrix A: the column space of A and null space of A, column space of A and null space of A transpose, column space of A transpose and null space of A transpose, column space of A and column space of A transpose. Yeah, so it is B, the column space of A and the null space of A transpose. They are orthogonal complement to each other. Okay. Let V be a finite dimensional inner product space over, and let W is a subspace of V. The orthogonal complement of W is denoted by W verb. Suppose you are given a vector V that belongs to the complement and vector U that belongs to W. Which of the following statement is necessarily true based on the definition of orthogonal complements? Yeah, so it is V. So as per the definition, every vector in V will be perpendicular to every vector in U. So their dot product will be 0. So there is a subspace W it's a subspace of V, and W perp is the orthogonal complement. Then the intersection of these two will be equal to, the intersection is what is the common element between these two? Yeah, so the intersection is the zero vector. Intersection is the zero vector. So W is a subspace of a finite dimensional vector space V, and W perp is the orthogonal complement. Then which of the following is true? The dimension of W plus the dimension of W perp can be less than the dimension of V. W is W perp the whole perp. The dimension of W plus dimension of W perp is greater than the dimension of V. Dimension of W can never be equal to the dimension of V. Yeah. So there are two theorems. One is this dimension theorem. For orthogonal complement. That is, the dimension of W plus the dimension of its orthogonal complement will be equal to the dimension of vector space V. Then another one is the double orthogonal complement. The double orthogonal complement theorem. That is, the dimension of the W will be equal to W perp. That is, when you take the orthogonal complement twice, it will give the W. Taking the orthogonal complement twice yield the same subspace. Okay. So then, based on this, what is the correct option among this? Which one is true? So the double orthogonal complement is the right answer. So the dimension of W, yeah, so like she told, the vector space itself can be its subspace. So when you take the dimension of, so if this are the same, then the dimension of W will be equal to the dimension of V. But in that case, what will be the orthogonal complement of W? So in this case, if you assume that the dimension of W and dimension of V are equal, what is the W complement? Yeah, 0. So then in that case, the dimension of W can be equal to the dimension of V. So it's not like dimension of W can never be equal to dimension of V. So that is not true. Uh, Coming to the concept of projection. So any vector, it will have a parallel component and a orthogonal component. So yeah, so when you take this vector u and vector v, and you want to find the projection of this v along u, then you can drop a perpendicular to the vector u, and that is this v minus ku, where k is this scaling factor of u, and this is that distance v minus ku. Now, this is perpendicular to u. So when you do that, you get an expression for k, which is v times u by u into u. Now, to find what is the projection, that is this one, ku, you just multiply it by that. So you get the orthogonal projection of v along the direction of u. And that is this expression that is given. V times u into u divided by u times u. So, we came across the concept of dot product, that is inner product. There is another thing that is called as outer product. That is, so inner product will always result in a scalar value, but outer product will always result in a space that is higher than the current one. So if you have two vectors, it will result in a matrix. So that is, it will multiply a column vector by a row vector to yield an n by n matrix. That is like this. So you have u1, u2 and u1, u2. So u1 into u1, u1 into u2, then u2 into u1, then u2 square. Okay. Now, so we got the expression for the projection of V along the direction of U. We can rearrange this to get a projection matrix. That is, you rearrange the U so that you get an expression like U transpose by U transpose U, and U transpose is a outer product. So it will result in a matrix, and that is given by this P, which is the projection matrix. Now there are some important properties for this projection matrix, that they are symmetric. That is P, when you take the transpose of this projection matrix, you get the same matrix. Another is this idempotency. That is, when you take the square, you get the same matrix. P square is P. And that has a meaning, that is, when you project a vector, it will already yield the same vector. That is, suppose you have a vector PV and you want to project it. So you multiply it by P, and that will be V, because it satisfies the idempotency property. So one question is, uh, suppose there is a vector V 3, 4, and we want to project it to the vector U, then what is the orthogonal complement? First, maybe you can find what is the projection matrix. Not the projection matrix, is this part. So this is the orthogonal complement. This one. So to find this, first you have to find this one. What is this one? V times U by U times U into U. Then to find the complement, you subtract this with U. So this is the orthogonal complement. P is 3, 4 minus 11 by 5 into 1, 2. You get 3, 4 minus 11, 1 by 5, 11, 22. So when you subtract this, you get an expression. 3, 4 minus this is the alternate problem. 3 minus 11 by 5, 4 minus 22 by 5, 4 by 5 minus 2 by. Now the next question. So you have a three-dimensional vector u, which is 1 minus 1, 2. Compute the 3 by 3 projection matrix P. What is the projection matrix here? So the projection matrix is given by U into U transpose by U transpose U. So you have to do the outer product. So 1 into 1, 1, minus 1, 2, minus 1, 1, minus 2, 2, minus 2, 4. What is U transpose U? 1, 1, 2, 2 plus 4, 6. So 1 by 6 times 1 minus 1, 2, minus 1, 1, minus 2, 2 minus 2, 4. Hmm. Now to show the symmetry, you just have to take this matrix, show that the transpose is equal to the matrix itself and the square is. Mm. So you have a vector u, which is minus 2, 3. The projection of u in the direction of the vector v is equal to 1, 0. V is 1, 0. Then what is the projection? Is minus 2, 0. So it's a direct substitution of the formula. This one, fourth question. The projection matrix P is always symmetric, idempotent, orthogonal, both symmetric and idempotent. Yeah, so it is both symmetric and idempotent. Now let's do this third question. So you have u is equal to 3, 4. The unit vector that is orthogonal to u is, so among this four option, which is the vector that is orthogonal to u? When it is orthogonal, u into v will be equal to 0. And it is given the vector is unit vector, so that also you should check. It's really a unit vector also. Yeah, so the option is C. Uh, it's so the option A and B are the same. And B ratio is just root 5. If it has to be a unit vector, it has to be 5. So the correct answer is C. Yeah. So there's a vector space. This question will do. There's a vector space R2, and the mapping is UV is U1 V1 minus U2 V2. Which of the following properties of inner product does the mapping not obey? Its commutativity. So the reference textbook, I hope it is given in the uh, course description as well. So you can check that. Otherwise, for example, for linear algebra, you can watch Gilbert Strang's videos or textbook. This one I have a doubt. I'll check it and tell. Maybe this one we can do. The seventh question. W be a 2D space belonging to R4. What is the dimension of the complement of W? Yeah, so it is the dimension of W plus the dimension of its complement is equal to the dimension of V, and that is R4. So that is 4, and this one is 2. So it will be 2 plus 2. Okay, now let's do this one. Sixth question. Which of the following properties of inner product does the mapping not obey? So this one, the first one is UV, the symmetry, that is UV, UV is given by U1, V1 minus U2, V2. Then VU is given by V1, U1 minus V2, U2. You see this, these two are the same. So both the expressions are equal. So this mapping will obey option A. The question is which mapping it is not obey. Okay. So the first one is not there because it obey. Then the second one is the that is K times U V is equal to U V. So that's correct. So this one we can write it as K into U1 into V1 minus K into U2 into V2 as per this expression. Then the right hand side is UAV, that is U1 into K V1 minus U2 into K V2. Now if you rearrange, these two are the same. So this is the same. So this property is also it obeys the inner product mapping. Now the third one is greater than or equal to 0. So when you take that, you so this is the in dot product of the vector with itself. So that is u1 into u1 as per this definition. It is u1 into u1 minus u2 into u2, right? So that is u1 square minus u2 square. So if we take one example 0, 1, then what we get is this is the vector, then we get 0 square minus 1 square, and that is minus 1. So it is not greater than or equal to 0. So this is the property that is violated. So yeah, so in general for dot product, the definition is u1 v1 plus u2 v2. But here they have defined it as the inner product of two vectors is given by this expression u1 v1 minus u2 v2. So you are asked whether it satisfies all the property that are usually satisfied for in a product. So this one U1 V1 minus U2 V2, this does not satisfy this non-negativity property. So that is the question. Okay. Now this question will do 10th question. The matrix that projects any vector onto itself is which among this one? Yeah, so it is the identity matrix. Think- Now coming to orthogonal matrix. So a matrix is called as a orthogonal matrix if the column vectors have unit length and column vectors are orthogonal to each other and they satisfy this property. So if V is a n-dimensional vector space equipped with the inner product, a linear transformation is isometric if it prevents the if it preserves the norm of every vector. Uh, so the isometric property is satisfied if and only if the matrix is a orthogonal matrix. Okay. Mm. Now, sometimes the matrix you can orthogonalize a set of vectors. So a procedure, there are a sequence of steps that we have to follow for this, and that is the Gram-Smith orthogonalization process. So if you are given a set of linearly independent vectors a1, a2, etc. up to an, you can orthogonalize them by taking by doing the following. So first vector, you take it as u1 is equal to a1, and then you take the norm of that vector and make it a normalized vector by dividing by that norm. Then the second vector, you have to make it orthogonal to the first vector. So you follow whatever you have done in that projection thing. So you take a2 minus q1 into a2 times q1, where q1 is this u1 by the norm of u1, and q2 is after that you take the norm. Then for all the subsequent set of vectors, you repeat doing this and then you get a set of or a matrix that is orthogonal. Now you can also, if you have a n by n matrix A where you have linearly independent column, then you can factorize this into Q and R, where Q is the matrix whose columns are orthonormal and R is the upper triangular matrix that contains the projection coefficient. Now, why we have to do this QR decomposition is when you have a system of equation, say Ax is equal to B, where you have to find x. Then if you can uh, normalize this into q into r form, that is decompose the a into q into r, x is equal to b, where q is the orthogonal matrix and R is the upper triangular matrix. Now, for an orthogonal matrix, the property is that the inverse is equal to transpose. So, you have to find what is x to solve the system of equation. Now, to find this x, when you take this to the other side, when you multiply it, you get q inverse, write it. So, you have ax is equal to b. This is what you have as a system of equation. What you have to find is this x. So this is the same as what we have studied in our school. A1x1 plus A2x2 plus A3x3 is equal to same B1. Hmm. Then we have A1, A12, A13. Now A21x1 plus A22x2 plus A23x3 is equal to B2. So like this, we had a set of equation, and then we find this x1, x2, x3. So that is the unknown. Now here, this A11, A12, A13, A21, A22, A23, etc. This is this A, the matrix A. Now, if you decompose this matrix so that if there is a way to solve this x in a easier way, then one of that way is this QR decomposition. So you decompose the A into a Q matrix and R matrix, a product of Q and R. Then the advantage is that this is the orthogonal matrix. That means this is its inverse is equal to transpose. Now this is the upper triangular matrix. Okay. So the inverse is transpose. So now you have QR x is equal to B. You want to find x. So you multiply both sides by inverse. You get Q inverse B. So then you have Q inverse Q is I. So it will go. Then R x is equal to Q inverse B. Now for an orthogonal matrix, this inverse is transpose. So Q transpose B. So Rx is equal to Q transpose B. Transpose, you know that you just have to change the row to column. It's such a easier operation. Now, the left hand side, if you see, it is a upper triangular matrix. That means you will have a form in the end, which will be like this. But I'll write it like this: R11, R12, R13, R22, R23, R33. All the values above the diagonal will be 0. So this will be x1, x2, x3. Now the advantage is that if you have the matrix in this form, you can start with this one. So R33 into x3 is equal to a scalar value you will get after doing this. So suppose that is, let us assume that it is C1. Then you can find x3 is C1 by R33. Then once you find x3, you substitute it here, then you find x2. So like that, by back substitution, you can easily solve this system of equation. So that is the advantage of this QR decomposition. And for getting the Q, that is orthogonal matrix, if it's not already orthogonal, then you can do this Gram-Schmidt orthogonalization. So, I'll give a simple question. To apply the Gram-Schmidt to orthogonalize these two vectors A1 and A2. So for the first one, it is A1 by norm of A1. This is the first normalized. So that will be 3 by 5, 4 by 5. What will be Q2? So you have to follow this. So when you do this, you should get minus 4 by 5. You get minus 4 by 5 and 3 by 5 as Q2. Okay. So from the Gram-Schmidt, you got Q as 3 by 5, 4 by 5, minus 4 by 5, 3 by 5. Yeah, so there is this concept of basis extension. So there is the vector space V, and there is a subspace W with the dimension V. So to extend the basis to the entire vector space V, if the dimension of W is D, then you need to add K minus D additional linearly independent vector to make it to extend the basis of W to the basis of V. So these additional vectors, they are obtained from the orthogonal complement of this W, because the dimension of V is dimension of W plus the dimension of V complement. So that is the extension mean. And then, so suppose there is a vector X, and it belongs to the vector space V, can be decomposed into sum of two different components, that is in terms of the W vector and also the W complement vector. So the squared norm of that vector, that will be equal to the squared norm of its orthogonal complement. These are some properties or theorems Now, there is a concept of real symmetric matrix. Uh, Matrix is a real symmetric matrix if all its uh, values are real numbers and the matrix will be equal to its transpose. Now, we have studied the concept of eigenvalues in the last class. So, eigenvalues, if you take for a real symmetric matrix A, the eigenvalues of that matrix will be also a real number. Now, the eigenvectors that correspond to the eigenvalues of the real symmetric matrix will be orthogonal, and in that case, a real symmetric matrix is orthogonally diagonalizable. So that is this orthogonal diagonalization, which is given by this spectral theorem. So if you have a n by n real symmetric matrix A, where the eigenvectors are even equal to and the eigenvalues which are real, lambda 1, lambda 2, etc., then the matrix A can be expressed as a linear combination of the projection matrices that are formed from the eigenvector. Okay, so this is the spectral decomposition form. And one thing is, when we apply a transformation to any vector, we can write it in this form, like a projection matrix of their eigenvector. Ax is equal to lambda 1 into u1 u1 transpose by u1. So that means the vector x, when applied a transformation, it is projected onto a mutually orthogonal direction that are defined by the eigenvectors. Okay? And each projection component is scaled by its corresponding eigenvalue, that is lambda 1, lambda 2, lambda n. Yeah. Okay. So I hope I'm clear. So the rest of the things we'll discuss in the next class. There is a power issue here. So I'm joining from my mobile hotspot. Um, yeah, I think we can wind up today's session. So next week we'll discuss about the contents from week 4. And I tried to cover some of the previous year assignment questions as well in this session. So in the next week also we'll try to cover some of them, and some of them that have not covered in week 1 and week 2. We can do it once we finish the full linear algebra portion. I think that will be next week. So we can do that as well in the next session. Yeah, thank you all for attending the session. Yeah, I will share everything. The previous year assignment questions I have access as the TA, but you will not be. You can see the questions when I share.